Hello students, in this module, which is part 3 of our series on function spaces, we're going to discuss the ideas behind Laplace transform, the basics of Laplace transform, how it is defined and so on. Now, in order to do that, we first briefly recall what we did in the last module, wherein we discussed a Fourier transform. Okay. Note that a Fourier transform is a generalized version of a Fourier series. Okay, wherein in a Fourier series you are trying to expand a periodic function over some domain. Okay, let's say which is minus L to L. Suppose you have a function that's periodic. Okay. Let's try to draw a function that's periodic. Okay, let's say you have a function like this between minus L and L. Now what the Fourier series does is that this is a function which keeps repeating like this between plus L. This is the wavelength is 2L. Okay, so from plus L to plus 3L it will again go like this. Okay, and similarly from minus L to minus 3L it again repeats like this. Okay, so let me draw it slightly better. Okay, this is minus 3L and so on. So this is the part that we consider, but this gets replicated forever. This is a truly periodic function. So Fourier series is basically an expression of a periodic function in terms of sines and cosines. Okay, this is what we saw in the last module, and what we also saw is that if you were to generalize this to, suppose you wanted to say f of x is k equals minus infinity to plus infinity ck e to the I k pi x upon L. Okay, this is the Fourier series, and if you wanted to think of this as psi k of x, then we can write f of x as simply k equals minus infinity to infinity ck psi k of x. This is basically the idea of an eigenfunction expansion. Okay, of which Fourier series is a special example. It's a special case for periodic functions. So Fourier series is a special example of eigenfunction expansions applicable to periodic functions, where the eigenfunctions are either sines and cosines, or you can think of it in terms of their exponential form, e to the I k pi x by L. Okay, now if this is the Fourier series, what is a Fourier transform? The Fourier transform, a Fourier series as defined, is applicable only for periodic functions. If the Fourier transform is a generalization of a Fourier series to non-periodic functions. Imagine you have a function which is periodic in the domain minus t to plus t or minus L to plus L. You take the limit t tending to infinity, then this shape becomes non-periodic, right? So as you take the limit t goes to minus to plus infinity, this becomes non-periodic. Therefore you get the notion of Fourier transform. So the Fourier transform is defined in terms of a pair of equations, which is called a Fourier transform pair. Suppose I know what is f of x. F hat of omega is called the Fourier transform of f of x. This is the Fourier transform of f of x, which is minus infinity to infinity dx f of x e to the minus I omega x. And similarly, the inverse transform f of x is 1 over 2 pi minus infinity to infinity d omega f hat of omega e to the plus I omega x. Now there are a couple of remarks that I wanted to make in the last module itself regarding the notation for Fourier transform. The first thing is the coefficients that happen in front of these two in the Fourier transform pair. Here I have taken 1 over 2 pi to be here, and 1 there is nothing, so this is just unity here. In some other textbooks, or even in my own one of the other derivations, I might have had 1 over 2 pi root 2 pi in both these equations, in both the transform pairs. All these are equivalent. The key idea is that if you multiply the coefficients of this and this, they should be the product of the coefficients should be 1 over 2 pi. Now where the 2 pi occurs, whether it is occurring here, or it is split as 1 over root 2 pi here and 1 over root 2 pi here, that is completely up to you. There is that freedom, because this is all dependent on how you normalize the eigenfunctions. There is a flexibility there, but once you stick to one definition, you should continue with that in order to avoid any inconsistencies in your calculations. The second comment that I wanted to make is that the sign of the exponential, okay, this again can be slightly different in different textbooks. Remember that k goes from minus infinity to plus infinity, so I might have equally called it minus ik. Okay, so in some textbooks you may find that this is minus, this plus becomes this minus becomes plus, and this becomes minus. So the key idea is, again, the exponentials should occur with opposing signs in their arguments. If it is e to the minus I here, it will be e to the plus I here. If it is e to the minus I here, it will be e to the plus I here. So these are the two flexibilities you have in the definition of Fourier transform. Now the second point that I wanted you to remember about Fourier transforms is that Fourier transforms are defined, or Fourier transform is defined for functions that decay as x goes to plus or minus infinity. That is, suppose I have a function, so it's reasonably well behaved, so that as this is x goes to plus infinity, this is x goes to minus infinity, so f of x should go to 0 in either limits. Okay, this is a requirement in Fourier transform. The reason being that you are trying to integrate, in order to find the Fourier transform of f of x, you are trying to integrate over minus infinity to plus infinity. That is, x is varying over the entire domain. That means that the function should not blow up as x goes to minus or plus infinity. Okay, so the Fourier transform is defined in some sense for well behaved functions. By well behaved, I mean functions that do not blow up as x goes to minus or plus infinity. Now the other comment I wanted to make is the Fourier transform is defined usually for functions that are spatial periodic. Okay, let me take a step back. The Fourier series, which is for periodic functions, can be defined for both of functions of time and functions of space, because you can have oscillations which are functions of time, and you can have oscillations which are functions of space, and of course you can also have oscillations which are functions of both space and time. Okay, so if you have a truly periodic function in space or time, you can use Fourier series. Now when you come to Fourier transforms, which is for non-periodic functions, okay, now here, okay, the thing is, you can define a Fourier transform for non-periodic functions, but usually you do it for functions of space, okay, because for functions of time, usually what happens is you are trying to use these Fourier transforms, or these transforms. These are more generally called integral transforms, both Fourier and the Laplace transform that we are going to discuss. Okay, These are used to solve differential equations. You know already from your earlier courses on process dynamics and control that Laplace transforms are used to solve ordinary differential equations, right? Similarly, Fourier transforms can be used to solve either ordinary differential equations or partial differential equations involving spatial variables. Now, whenever you try to use integral transforms to solve differential equations, okay, the time variable comes with a special initial condition. That is, at some time t equal to 0, you say that the function f of t, takes some other value, right? Is f naught for t greater than or equal to 0. At t less than 0, the function is 0 or something. Okay, this is typically what we call as initial condition. Okay, in solving differential equations, you may say that you have a bar of solid which is at temperature T0, and at suddenly at time t greater than or equal to 0, the temperature at the ends is increased to T1, and then you are interested in understanding how the temperature changes as a function of time. And these are the kind of problems that you solve in heat transfer and transport phenomena, right? So basically the time variable occurs with an initial condition wherein the function typically can be, if the temperature is T naught, you can define the new variable to be T minus T naught, which is, let's say, T prime. So T prime will be 0 for T less than 0. So usually you have functions that can be rescaled or redefined to be 0 for T less than 0, and for T greater than or equal to 0, f of t is f naught, some other value. But this is not the case with spatial variables. Okay, so you use Fourier transform usually for functions of spatial variables. Now the transform that we are going to discuss, which is Laplace transform, is more suited for these kind of functions which are 0 for time t less than 0 and greater than or is equal to 0 for time t greater than 0. Okay, so suppose I show you a function like this. Okay. Now I say I have a function which is 0 until t less than or equal to 0, for t less than 0, and t greater than or equal to 0, the function takes a value f0 or 1. So this is f of t versus t. This is t equal to 0. This is function f of t is 0. Let's say f of t is 1 forever for t greater than or equal to 0. Now for this function, as t goes to infinity, the function does not decay. F of t does not decay to 0 as t goes to infinity. That means that cannot define the Fourier transform of such a function. Not just this function, you also have functions that appear like this. Suppose you have a function which is e to the lambda t, and lambda is greater than 0. The function grows exponentially. Again, f of t does not decay as t goes to infinity, so cannot define its Fourier transform. So what do you do with such functions which are, let's say, not so well behaved, in the sense that they do not decay to 0 as time t goes to infinity? Okay, how to get around and define Fourier transform? So let's denote these functions f of t. Okay, these are not well behaved functions in the sense that, and no Fourier transform exists. So how do we define Fourier transform? You cannot define Fourier transform, but you can modify this function in the following sense. You multiply f of t by e to the minus gamma t such that this product f of t times e to the minus gamma t goes to 0 as t goes to plus infinity. Okay, so even though f of t may be growing in time, gamma is sufficiently uh, large. Gamma is a positive number, that's negative sign, so that it decays to 0, the product decays to 0 as t goes to plus infinity. So you have solved one problem, that as 3t goes to plus infinity, this product is well behaved, even though f of t is not well behaved. But you have created one more problem. If you plot e to the minus lambda t, it will appear like this. So while this is e to the minus lambda t versus t. While it decays to 0 as t goes to infinity, it blows up as t goes to minus infinity. So there is a problem, because you cannot, in order to define a Fourier transform, you should have the function to go to 0 at both ends. So to avoid this problem, or to overcome this problem, you multiply by what is called the Heaviside step function, which looks like this. Okay, so this function is such that if for t less than 0 the function is 0, for t greater than or equal to 0 the function is 1. Okay, so this is called the Heaviside step function, or simply the step function. So this is denoted by h of t. H of t is 0 for this is t equal to 0, and h of t is 1. So if I consider this combination f of t, which is not well behaved, times e to the minus gamma t, which is well behaved as t goes to infinity, times h of t, this combination is well behaved as t goes to both, as t approaches plus infinity and minus infinity. Okay, so let's call this combination, this product, as capital F of t. Now we can take the Fourier transform of capital F of t, because it is well behaved. Now that is defined as the Laplace transform of small f of t. Remember that small f of t was that not so well behaved function for which we could not define Fourier transform. So we could take the Fourier transform of f of capital F of t, which is small f of t times e to the minus gamma t times h of t. So the Fourier transform of capital F of t, which is this combination, is defined as the Laplace transform of small f of t. That is the definition of Laplace transform. Okay, now right, so now let's define. So the Fourier transform of f of t is denoted as f of omega, right? F hat of omega. So f hat of omega is nothing but minus infinity to infinity f of t e to the minus I omega t dt. Okay, now f of t is 0 for t less than 0 because of the Heaviside function. So I can split this integral into two parts, but f of t is simply f of t e to the minus gamma t. So I have to just put f of t e to the minus gamma t. This is 0 here. Okay, e to the minus I omega t dt. So this part goes away, 0. Okay, now so this can be written as 0 to infinity. Now I can combine this two exponentials, e to the minus gamma plus I omega times dt. Okay, now let's call this combination gamma plus I omega as s. This is called the Laplace variable. Okay, and if I do that, now I have to I already told you that the Fourier transform of f of t is the Laplace transform of f of t. So the Laplace transform of f of t is denoted as f of s, small f of s. Okay. Therefore, f bar of s, that's the usual notation. If you know from your earlier courses on process dynamics and control, you typically use a over bar for Laplace transform, right? So 0 to infinity f of t e to the minus st. This is just from the previous expression. I'm just calling this combination as s. Okay, and this has now become f bar of s. Okay, so once you do that, now times dt. Okay, now we have to look at the inverse transform. So this is the definition of Laplace transform. Okay, so this is the fundamental definition of Laplace transform. Laplace transform of f of t is f bar of s, which is obtained by integrating 0 to infinity f of t e to the minus st dt. Okay, now what is the inverse transform? Again, we appeal to the Fourier transform idea. Is f of t is 1 over 2 pi integral minus infinity to infinity f hat of omega e to the I omega t d omega. Okay, but what is capital F of t? Capital F of t is nothing but small f of t e to the minus gamma t for t greater than 0. For t less than 0, anyway that function is 0. So this is nothing but, okay, right, because we know that small f of t was written as e to the gamma t, capital F of t, right? So capital F of t is small f of t times e to the minus gamma t, right? So f of t times e to the minus gamma t is equal to 1 over 2 pi minus infinity to infinity f of omega, now f of omega e to the I omega t d omega. Therefore f of t is, I can multiply by e to the plus gamma t on both sides, is 1 over 2 pi minus infinity to infinity f of f hat of omega e to the I omega t plus gamma t d omega. Now f of t, but this is nothing but I times gamma plus I, sorry, t times, okay, this variable is what we called s. So f of t is 1 over 2 pi minus infinity to infinity f of omega e to the st d omega d. Okay, s is gamma plus I omega, so ds is nothing but I d omega, or d omega is nothing but ds by I, right? And f of omega, f hat of omega is the same as f bar of s. Okay, that's what we defined as the Laplace transform of f of t. So f of t, which is the inverse transform, is given by 1 over 2 pi. Now the variable has changed from omega to s. Omega is minus infinity, s is equal to gamma, sorry, minus I infinity to gamma plus I infinity. Okay, f s, f bar of s e to the st ds by I. So I'll take the I outside, 1 over 2 pi I. Okay, so this is called the inverse transform, inverse Laplace transform. Okay, so obviously this is something that we have seen earlier when we try to show that how this can be, the residue theorem can be used to invert Laplace transform, right? So this is something that we have seen already, but this expression, but I had not shown you how this expression arises. So just to recap, the Laplace transform is a special or a generalization of a Fourier transform. The Laplace transform is a generalization of a Fourier transform in that it is a one-sided Fourier transform, one-sided and weighted, because you are weighting it by the Heaviside function. You are weighting it by e to the minus gamma t. It's one-sided because you are multiplying it by the Heaviside function. Okay, Fourier transform of less well-behaved functions. Now, so if you look at the Laplace transform pair, let me write the LT pair, just like we had the Fourier transform pair, right? LT pair is like this: f bar of s is 0 to infinity, f of t e to the minus st dt, and then f of t is minus infinity to infinity 1 over 2 pi I, right? F bar of s e to the st dt. Now, in general, s in the inverse transform, s is, you are trying to, I have to be very careful about the limits. This is gamma minus I infinity to gamma plus I infinity. That means that if you look at the complex plane in S, this is real part of S, this imaginary part of S. So let's say gamma is here, this is gamma minus I infinity, this is gamma plus I infinity, right? So this is the path in which you are trying to integrate, right? So this is the path in which you are trying to integrate. It's a straight line, but that shifted away from the real axis. So in order to do this integral, we said that we can close the contour to the left, okay, and naturally the definition of Fourier Laplace transform takes into account the fact that the function f of t is 0 for, okay, this is already built in. So when you do this inverse transform by closing the contour in this direction, it is automatically, you are guaranteed that the function will be less than, for the function f of t is 0 for t less than 0. Okay, so that is automatically built in the definition of Laplace transform, as we had discussed earlier, right? So this is very, very useful in the solution of ordinary differential equations. Again, just to remind you of the advantage of both the transforms, Fourier and Laplace transforms. What is the advantage? The advantage is that, as I showed you in the last module, the time derivatives or spatial derivatives become algebraic quantities. Okay, this becomes, and typically in Laplace transform, this becomes s times f bar of s. This is minus I k times f hat of k. Okay, the Fourier transform, here it's a Laplace transform of df by dt will be simply multiplication of the Laplace transform of the function times s. The Fourier transform of df by dx becomes simply multiplication of the Fourier transform of the function by ik. This means that at least if you have differential equations of the form d squared dx squared, they become algebraic expressions because you simply have minus k squared. Same with Laplace transforms. So that means that you can solve you can reduce the complexity of solution of differential equations to the level of solving just an algebraic equation. Okay, so you are no longer solving differential equations, you are solving only quadratic polynomials or cubic polynomials. That is the advantage of both Fourier and Laplace transform. And remember again that where we started off from, whenever we started off in order to define Fourier transform, Fourier series, is the simple notion of expansion of a vector in terms of the basis vectors in finite dimensional space. This got generalized to expansion of a function in terms of the basis functions. Okay, and for periodic functions, this became the Fourier series. The general idea of eigenfunction expansion. And for non-periodic functions, the Fourier series generalized to Fourier Transform. And for functions that do not decay as t goes to infinity, then we had to modify the Fourier transform, and we defined the Laplace transform, which is a weighted one-sided Fourier transform, which is specially used for solving initial value problems. Okay, so I will illustrate how Laplace transforms can be used to solve differential equations in when we do differential equations. But right now, my idea is to show how Laplace transform came about, and all this can be understood from this logical train of thoughts, from this basic idea of expansion of a vector in terms of basis vectors or orthonormal vectors, to functions in terms of eigenfunctions, to Fourier series, to Fourier transform, to Laplace transform. This is a very, very compact way of understanding how all these ideas are connected. Okay, so students, I'll stop here and I'll continue in the next module.